Let's look at this variation on the factorial program using a different code editor. The program prints both the value of n and n factorial from 2 to 20. It initializes factorial to be 1, and then each time through the loop we multiply by the next integer, which gives us the factorial for that value. Inside the loop it outputs both the value of n and n factorial. By putting the print inside the loop, we can see how the factorial result is accumulated each time through the loop. When we run it, we see that the factorial program grows very quickly, and at 13 is already over 6 billion. Python's int type can handle very large numbers automatically. Many programming languages do not automatically handle large integers. Let's look at the same program written in the C++ language. We won't worry about the details of the syntax, but you can see the accumulator pattern where we initialize the variables and then use a for loop and update factorial each time through the loop. When we run it, the first few numbers look fine, but note that 13 factorial is not over 6 billion. This is because of the way computers represent numbers using zeros and ones. The largest unsigned number that can be represented with 32 bits is a little over 4 billion, so once the numbers get bigger than that, the result is invalid. If we change the C++ program to use a type that can represent both negative and positive results, we get even stranger results. Note that some of the values are now negative. Next, we'll take a basic look at how computers represent integers so we can see why this happens in C++. A bit is defined as a single 0 or 1. A byte is a group of 8 bits. Most modern computers process either 32 bits, which is 4 bytes, or 64 bits, which is 8 bytes, at a time and use that many bits to represent an integer. With 1 bit you can store 2 values, either a 0 or a 1. With 2 bits you can store twice as many values, as you have the patterns 0, 0, 0, 1, 1, 0, and 1, 1. Add a third bit, and we now have 8 values we can store. We can place a 0 in front of the above 4 values, and we can also place a 1 in front of the above 4 values. That's why every bit you add doubles the number. Of values you can represent, as we could use the same process when we add a fourth bit. So with 32 bits, we can represent the numbers from 0 to a little over 4 billion. The number we can represent is exactly 2 to the 32nd minus 1. The reason it is not 2 to the 32nd is 1-bit pattern is used to represent the number 0. If we also want to represent negative numbers, we need to use half the patterns for the negative values. So the range is from about negative 2 billion to about positive 2 billion. And the exact range is negative 2 to the 31st to 2 to the 31st minus 1. Note there is one more negative value than positive value, as 0 uses one of the bit patterns for the positive numbers. Next we'll look at using 3 bits to represent integers, and this will help us to understand the strange results we got from the C++ factorial program. We generally use what is known as base 10, which uses the digits from 0 to 9, and the columns from right to left are the ones column, the tens column, the 100s column, and so on. Computers use base 2, so the digits are 0 and 1, and the columns are 1, 2, 4, 8, and so on. This diagram shows the non-negative values we can represent in base 2 with 3 bits. Note that there are 8 values, which is 2 to the 3rd power. If we add 1 to the last bit pattern, which is 7, the result will wrap back around and we will get 0. If we multiply 6 by 2, we could accomplish the same thing by adding 6 to 6. If we move 6 places from 1, 1, 0 wrapping around, 1, 2, 3, 4, 5, 6, we end up at 1, 0, 0, which is 4. That is why the C++ factorial program gave strange results once we passed about 4 billion, as it wrapped around once it got past the largest number that could be represented with 32 bits. This shows the bit patterns used when we represent both negative and positive numbers. 3 is the largest positive number we can represent, and if we add 1 to it, we would get negative 4. This is why the C++ version that used both negative and positive values sometimes resulted in negative values once we passed about 2 billion. Fortunately for us, Python automatically uses more bits as the numbers grow larger, so we do not need to worry about this when writing code in Python.